Hi, in this presentation I'll talk a little bit about how colors are represented on a computer. And there's basically two schemes for representing colors. The first one, and probably the one you're more familiar with, is what's known as additive colors. So additive colors are, they're red, green, blue. The components of additive colors, there's red, green, and blue, denoted R, G, and B. And we think of starting with a black surface and then adding in red color, green color, or blue color. And this is typically what happens with any kind of computer display, CRTs or LCD monitors, projectors, anything that's generating light that you're looking at. You start with a black surface, TVs, I should say TVs. You got a black surface like the screen of your TV, and it lights up pixels that you then see color. And so the pixels have subpixels that turn on selectively red, green, or blue. And then what you see is a combination of the red, green, blue, and your eye interprets that as a blended color. So basically, in this setup, we start with black, and then we add in red, green, and blue in varying amounts. And we think of red, green, and blue usually as being in the interval 0, 1. So full brightness like red 1, green 1, blue 1 would be white, and so forth. These are the so-called additive colors. There's also the subtractive colors. And if you've worked in photography or film, for instance, or printing in general, you might have come across subtractive colors. So in subtractive colors, we start with white and we subtract out certain colors. Now the colors we use for subtracting out are cyan, denoted C, magenta, denoted M, and yellow, denoted Y. So cyan, I'll show you an image in a moment, is like it's a light blue looking color. So if you looked at it and someone asked you what color is that, you'd probably say blue, but it's a light blue. It's rather different than the blue in the additive colors. The blue in the additive colors is a very dark blue, maybe almost a purplish even. But this is typically a very dark blue. Cyan, I think of it as a light blue. Maybe a better way to say it is a combination of the green and blue from the additive colors. Magenta, so all right, this is like a light blue, really a combination of the green and blue from the additive colors. Magenta is like a reddish blue. It's really, and yellow is yellow, right? So yellow is somehow subjectively a completely distinct color than anything else. And these, in this setting, we start with white and subtract out colors. Well, what colors do we subtract out? For cyan, we subtract out red. Cyan is the opposite of red. For magenta, we subtract out green. And for yellow, we subtract out blue. And so the picture with the subtractive colors is you've got a white light shining, think of it shining through something. So this is used for film, for paint, for printing with inks, painting with inks. And all of these have the following property. With film, you're shining light through a film. You have a pure white light, you're shining it through a film. Some of the light gets absorbed by the film and isn't passed through. Some of it passes through. And so we're subtracting out certain lights to generate the color cyan. To generate the color cyan, we would subtract out the red light. To generate the color magenta, we would subtract out the green light. To generate the color yellow, we would subtract out the blue light. For painting or, I wrote that twice there, but okay. For painting or printing, we have inks or paints on a paper. White light is shining onto the paper and being reflected off. Some of it's being, however, absorbed and that's, in other words, subtracted out, and some of it's being reflected off or not subtracted out. And so if you're looking at a surface that's been printed and it looks yellow, that means that you've subtracted out the blue part of the light and reflected the rest of the light. So the conversion here, as you think of cyan, is going to be subtract out the red, magenta, you subtract out the green, and yellow, you subtract out the blue. This actually gives us a nominal way to do conversion here. In the additive setting, RGB are in the interval 0, 1. So here we're also going to have C, M, and Y are in the interval 0, 1. And the formulas are C is 1 minus R, M is 1 minus G, and Y is 1 minus blue. And this is sort of a nominal conversion. If you have RGB colors, you can nominally convert them to CMY colors by these formulas. I say nominally because it doesn't work super well. It's hard to make the translation between these two things just because the colors don't, they're different physical bases, and therefore the colors don't quite correspond so simply as these formulas would make it look like. Let me get a little bit more into how CMY subtractive colors are used. In practice, people actually don't use CMY. They use something called CMYK. And if you ever bought an inkjet printer, for instance, you may have seen this. You have 4 ink cartridges that you have to buy for your color inkjet printer. There's looks like blue, red, and yellow, CMY, but there's also pure black. So this is cyan, magenta, yellow, and the K stands for black. And the idea here is that black should nominally be a complete mixture of cyan, magenta, and yellow. So in principle, mixing C, M, and Y, namely with, think of C equals 1, M equals 1, and Y equals 1, should give black. But in practice, it's hard to choose actual physical inks for cyan, magenta, and yellow, such that both they look good for mixing lots of colors and they also generate a really good black color when you mix them together. So what people do when you're printing is you use special black ink when you want to get black colors, and when you get other colors other than black or gray, you would use a mixture of CMY. It also saves on ink because if you have a nice black ink, you don't have to use so much of your other color inks. And for high quality printing, if you go to a professional printer, for instance, or glossy magazine printers or something like that, they actually use more colors than this. They use 7 colors. There's C, M, Y, K, plus OGV. There's 3 more types of ink, which are O for orange, G for green, and B for violet. And this gives the printer the ability to generate a lot more different colors. If you recall before, we saw that triangle. I'll show it to you again in a moment here. We saw that triangle, and it didn't cover, with corners labeled red, green, and blue, it didn't cover the entire visible space. By using more colors, OGV, you can color more of the visible space. This is also used in the RGB setting. In the RGB setting, there's also various extensions to more colors. So, for instance, some Sony brand cameras use 4 colors instead of 3. They use they use RGBE, where E stands for emerald. Okay. And they actually have 4 different types of light receptors, or 4 different types of filters on top of their light receptors to get different, be receptive to 4 different wavelengths. That's converted back to RGB when you use it in your computer programs, but the camera itself is gathering more detailed information on the color. Some TVs use RGBY, where adding yellow in. The yellow here is actually just estimated when it's displayed on the TV, because there's no broadcast colors. Broadcast colors or colors on your HD TV signal only include RGB values. They don't include yellow values, but the Sony TVs, and the Sharp and Sony is the brand that does this, I guess. Those TVs estimate a yellow color and display that as well. So let me show you a couple pictures on the computer for this. In this first image, we see on the left-hand side, part A of the figure, the illustration how the RGB additive colors combine. Here we see 3 large circles. One of them is red, one of them is green, one of them is blue. Think of these as being lights shining towards us, transparent lights shining towards us. There's a black background where there's no light coming at us, it's black. Where just the red light is shining towards us, we see red. Just the green light is shining towards us, we see green. Or just the blue light is shining towards us, we see blue. Notice this is a nice dark blue. Where all 3 colors overlap in the center, we have full brightness from red, green, and blue. We just have a white color. Where the red and the blue overlap, we have magenta. Where the blue and the green overlap, we have cyan. Where the red and the green overlap, we have yellow. On the right-hand image, we have the subtractive colors. So here, think of a white surface that we're looking at, and we have, say, circular paint put down. There's a circle of cyan-colored paint here, circle of yellow paint here, a circle of magenta paint here. So where there's no paint, of course, we see white. Where cyan and magenta overlap, we see blue. Where magenta and yellow overlap, we see red. Where yellow and cyan overlap, we see green. Where all 3 of them overlap, we're subtracting out all the brightness, all the color, and we just see black. This image comes from the Wikipedia page for color space. It's listed on the side window. This image is due to Ben R.G. and CMG Lee. And the main thing I want to show you here is what the RGB color space looks like compared to the total amount of visible color space. The whole colored area on this thing, this sort of oblong half ellipse kind of thing, represents, in principle, what colors are visible to an average person. The triangles here, one of them is labeled sRGB, the other one's named color match RGB. They're very similar to each other, represent approximately what can be the range of colors that can be shown on a monitor or a typical RGB-based display. There are some larger spaces. There's the Adobe RGB and the ProPhoto RGB, and also the SWOP CMYK standard for CMYK. This shows the colors that in principle are representable in a broader color range. Doesn't mean necessarily that any particular monitor or printing system matches all the colors in this region, but it does index into a larger portion of the viewable color space. So as you can see, there's, even in the most aggressive color space, there's still colors that are viewable to the human eye that can't be represented in these systems. Okay, now we'll return to the blackboard. Returning now to RGB, I'd like to discuss some of the typical ways that RGB values are represented on your computer. So, representation of RGB values. So, the usual way is the so-called 24-bit color or 32-bit color. This is probably the system you're most familiar with. On Apple, this would be called millions of colors, because 2 to the 24th is more than a million. And here we have, the system would be 8 bits plus 8 bits plus 8 bits plus possibly 8 more bits. And we would have 8 bits for representing red, 8 bits for representing blue, 8 bits for representing green, and possibly 8 bits for the alpha value or the transparency. And so together this would make either 24 or 32 bits. And in other words, the RGB values are integers in the range 0 to 255. And by dividing by 255, we get numbers in the range 0 to 1, which is how we've usually been representing these values. So that's 24-bit color. An older one, standard, is 16-bit color. Or on Apple, this would be called thousands of colors. Because 2 to the 16th is 65536, thousands. And here we would use 5 bits for red, 5 bits for green, 5 bits for blue, and 1 bit for transparency. So this is red, green, blue, and transparency. And finally, really old, is the so-called 8-bit color. Probably you don't have a system that supports this very much. And this uses 3 plus 3 plus 2 bits. So that's 3 each for red and green, and 2 bits for blue. Why fewer bits for blue? Well, your eye is less sensitive to the resolution of blue. You have fewer blue cones in your eye than you do red and green cones. So your eye sees less detail in blue. So it does less harm to the quality of the image to reduce the number of bits allotted to blue than it would to reduce the number of bits allotted to red and green. Of course, this means you've only got 8 possible settings for red, 8 possible settings for green, and 2 possible settings for blue. Still a total of 256 colors, or hundreds of colors, as Apple would have called it once upon a time. And it's still a fair number of colors. These, especially the first one, are the most common. There are, more modern, more recent proposals for more color. For instance, the UHD TV color standards allows either 10 or 12 bits per color. So it would be 10 or 12 bits for red, 10 or 12 bits for blue, 10 or 12 bits for green. So there is some definite movement towards having more colors available. The problem with having too many colors available in your representation is that it makes file sizes larger and makes, say, transmission over the internet slower and so forth. And so there's various other mechanisms to improve color resolution while keeping file size down. And the most prominent one of these is what's known as a color lookup table, or CLUT, CLUT for short. Color lookup table. And these are used for GIF files in particular, but also used in many other places too to keep the file size down. Now, GIF files also use some other compression techniques, LEMPL-ZIV methods, to keep the file size down. But an important part of their size reduction is they use fewer colors. What this does is each image has its own color lookup table. So it has a color lookup table, a CLUT, which contains typically, the parameters can vary, but it contains typically a table of 256 different colors, each either 24 bits or possibly 32 bits. So in other words, with 24-bit color, we'd have 256 different colors, each with 8 bits for red, 8 bits for green, and 8 bits for blue. And then the pixels in the image have a 8-bit index into the table. And so the pixel has the number of the entry in the color lookup table that's the color of that pixel. And in this way, we only need one table, and then no matter how big the picture is, we only need 8 bits of information per pixel to store the color for that pixel. The colors in the table are tailored to the colors in the image. So each image has its own lookup table. So if you have an image, say with a lot of green colors and less, say, other colors, the color lookup table will have a lot of subtle different colors of green. And so in this way, we can still get acceptable color appearance in the image, even with only 256 distinct colors. This would not have been possible so easily in the 8-bit color that I described on the previous board. So the big advantage here, though, is this save space. And that's everything I wanted to say about representation of colors. That's the end of this presentation. Thank you very much.